Hello, everyone. So my name is Joan Xiao. I'm a lead machine learning scientist at Figure 8. I'm very excited to be here to talk about deep learning for product title summarization. So first, just a brief introduction about Figure 8, in case you have not heard of us before. So we are a human in the AI, human in the loop platform for data science and machine learning teams. We empower them to train, test, and tune the models and make AI work in the real world. And the agenda is as follows. So first, we'll talk about the motivation of this problem. And I'll introduce two deep learning-based approaches. And I'll share our implementation details, and then finally the results. So first, let's talk about, why do we need product title summarization? You would think that product titles usually are already short enough. What's the need for making it even shorter? So here is a headline of an article on TechCrunch in March 2018. So due to the growing popularity of smart speakers, voice-based shopping is estimated to grow to $40 billion plus across US and UK by 2022, up from $2 billion currently. So let's see if I ask my voice shopping assistant for a product, let's say laptop, backpack, what will be returned from some of the leading e-commerce websites. And here it is. I enter the keyword for laptop backpack, and these are the two top search results. So as you can see, each of them is at least 30 words long, and I tried to speak one of them. It took me 25 seconds. So for the consumer, you can understand that it will be very difficult to capture the essential information of the product at the end of the 25 seconds. So for better user experience of voice-based shopping, we need descriptive but short titles. So here is one of those examples again. So on the left side is the original title, and we want something that's short, but still describe the product so that we know what we want to do with the product. So if you look at the title, well, you see that, okay, the cursor seems to be important, right? It identifies the brand name. And also the laptop backpack that describes the function of the product. We should have that in the title as well. Among the rest of the words, I would say the gray, the color is important. It's an important factor for the consumer to make a decision as well. So if we just put those three words together, we come up with a pretty decent, good short title. So that's going to be our goal. So first, let's talk about how we're going to approach this problem. Again, this is the previous slide. So on the left side is the original title. On the right side is what we want the short title to contain. And as we discussed earlier, we knew that cursor actually is the brand name, and laptop backpack is the function. Gray is a color, but I'm making it more general, calling it a variation, because sometimes it could be like different materials, or it could be for different age groups. So for those of you who have worked with, or who are familiar with named entity recognition, you may have said to yourself, this sounds like a named entity recognition problem. And you're exactly right. So that's our first approach. We are going to use named entity recognition to solve this problem. So named entity recognition also shorthanded as NER, also called entity chunking, entity extraction. It's a subtask of information extraction. It basically locates named entities in the text and classifies them into predefined categories. So there are common categories such as person, organization, location, etc. And here's one example. So I'll give you a second to read the sentence. So in this sentence, Facebook, Twitter, and Google, they are identified as org, short for organization, and browsers as location, Monday as a date. So traditionally, the NER problem have been solved originally using rule-based approach. Basically, you handcraft a bunch of linguistic rules or grammar rules. And later, people started using supervised learning with the algorithms ranging from distinction trees all the way to hidden Markov models and conditional random fields, with conditional random fields being the most popular one. But with supervised learning, traditional learning, you would have to do feature engineering, right? You have to create features such as word-level features, the length of the word, the context of the word. You could also use document features. So you have to basically, in order to create a good NER system, you need to spend a lot of time on feature engineering. So now welcome to deep learning. Deep learning can use nonlinear activation functions to capture complex relationship. And so next, I'm going to go over very quickly a few common neural networks in NLP. So first, the CNN. We all know CNN is what makes computer vision take off, right? Because we have been able to obtain superhuman accuracy on image classification. But CNN can also be used for text problem in NLP. So this is the picture of one layer CNN that achieved state-of-the-art result on 4 out of 7 text classification tasks in 2014. But for most of NLP problem, you need to use RNN because you have variable length of input. So here is a picture of the RNN, which basically is the one layer RNN. However, vanilla RNN suffers from the vanishing gradient problem. So to address that, we use LSTM or GRU. Here's an example of LSTM. But these networks, as you can see, right, the arrows only flow in one direction. So you can only use information from the past state. You cannot use any future state in your input sequence. So then we use bidirectional RNN. Here is an example of a bidirectional LSTM. So with this network, you can use information anywhere from your input sequence. But then the drawback is the input and output, they have to have the same length, as you can see from the picture. So to overcome that limitation, people started using encoder-decoder RNN. This is common in the machine translation world because your input and output are typically of different length. So this network actually works well for short sequences, short sentences, but for long sentences, the performance is not good. As intuitively, you can see that we as humans, we don't do translation this way. We don't read the whole sentence and then memorize and then try to translate it, right? So that just doesn't work well with long sentence. So next network that we have been using is this bidirectional encoder-decoder RNN with attention mechanism. So at the bottom is the bidirectional RNN RNN network we saw earlier. But there is on top of that, there is an attention model which calculates a set of weights that represents the amount of attention that needs to be paid to each word in the input sequence. And these combined weights are fed into the decoder and the output, which outputs the word in the output sequence. So this actually becomes very influential, even though this was studied in machine translation, but it has been used in several other NLP problems as well. And in this example, we use attention model to augment our RNN network. You can actually also use attention with CNN as well. And even more, you can use a model that has attention model only. So last year in 2017, a research team at Google, they published a paper, Attention is All You Need. They introduced a very simple new network architecture, which is called a transformer. It does not use any of the recurrent or convolution network. And it achieves state-of-the-art result on machine translation. And this actually also has become the core of the current new trend in NLP, as we will see in a moment. So for those who have been working with NLP problems over the last few years, you probably have used pre-trained word embeddings such as word2vec or GLOV. So these embeddings are great, right? They have helped us improve the NLP system significantly. Unfortunately, we have only been able to use them to initialize the first layer of our model. If you want to train a good NLP system, you still need a lot of training data. So now there's this new trend in NLP that is to pre-train a language model, and then you can fine-tune the whole model and on your target task. And these have achieved state-of-the-art results on many NLP tasks. And here is a few examples of them. So EMO stands for embedding from language model. Is a deep contextualized word representations. So this is a bidirectional language model was trained on very large corpus. ULM fit, universal language model fine-tuning. In this paper, they introduced several very important techniques for fine-tuning a language model, including gradual unfreezing and discriminate fine-tuning. And OpenAI's GPT, I guess it stands for generative pre-training. So it's actually purely transformer-based. And the BERT, bidirectional encoder representation from transformer, this was just released 2 weeks ago by a research team at Google. This is also purely transformer-based. It's a deeply bidirectional language model. So all of these have achieved state-of-the-art results on many NLP tasks. And so in contrast with what we have been doing, right, we have been using pre-trained word embeddings. So in the future, you can probably just use these pre-trained language models, and hopefully you can achieve much better result with your problems at hand. So I highly encourage you to take a look into this for more details. So back to the NER problem. So deep learning has achieved many promising results on NER. So this is the latest results, the current best results on Cornell 2003, which is a public data set of newswire text that's commonly used for NER problem. So as you can see, starting from 2011, people have started using CNN. And since then, just more and more research have been done, and then more and more network have been created, and the new results have been achieved. So now let's switch gear to our second approach, which is text summarization. So after all, it's a summarization problem, right? So text summarization is a task of producing a short but concise fluent summary while preserving the meaning of the original text. And there are two types of summarization. One is extractive, the other one is abstractive. So extractive meaning that you identify key sentences or keywords, and then you extract them, you compose a summary without modifying the original text. Abstractive is actually to generate a new, shorter text, which still needs to preserve the original meaning. So in general, abstractive is, they look much better because they do a nicer job on condensing the text than extractive. But then on the other hand, it's also much more difficult to do because it requires semantic representation, natural language inference, and generation. Also, I just want to mention quickly how we evaluate summarization models. So human evaluation is a very common method because you want to ask human to evaluate the grammatically, whether it's grammarly, whether it's correct, whether there are any redundant words, or whether it's actually integral to the original meaning of the text. And there's one systematic metric for evaluation is called ROUGE, which stands for Recall-Oriented Understudy for Gist evaluation. So basically, it calculates percentage of overlapping n-grams. So you will see like ROUGE 1, ROUGE 2, ROUGE n, whatever n you want to use. It's basically it's counting the n-grams in your ground truth reference summary, how much overlapping, how many of them actually occur in your summarization generated output. And there's a Rouge error, which is based on longest common subsequence. So here is the current top results for text summarization on GigWord. English GigWord is a common public data set, also consists of newswire text. So all the current top results are used deep learning, and all of this also came out from 2018. So as you can see, this is equally exciting in the text summarization field as well. So next, we're going to talk about our implementation details, like how did we summarize the product titles. So our first approach was NER. So for NER, of course, you have to obtain labels. So given one title, like the original title, which is a bunch of words, so for each word or token, you would have to obtain a label on whether this is an entity or not. If it's an entity, then does the entity have multiple words? So what you see in the label, in the like, table format in the middle is it's called a BIO type scheme. BIOB stands for beginning, I for inside, O for outside. So if it's an O, meaning it's not an entity. So any entity will have a B tag because it's the beginning of the tag. And if an entity has multiple tokens, then you will see after the B tag, you can see one or more I tags as well. So we obtain the labels for the so we have a data set of about 56,000 product titles, and then we split it into training, test, and the validation set, and we obtain entity labels, and then we train the model. So the model will predict whether, for every title, whether the word is an entity or not. And for those predicted as entities, we just extract those words and then compose a show title, as you see on the screen. So for the summarization approach, so we use the same ground truth label from the NER problem, but then we just compose it as a show title instead of using individual entity tags. And then the model will take the input, which is the product title, and the output will be the show title itself. And it will, of course, the prediction is supposed to be a show title. And here is the architecture of the model. So we use the same architecture for both approaches, just for this task. So it's a pretty basic bidirectional LSTM encoder and decoder with attention. And here are some of the hyperparameters. We actually didn't do a lot of tuning on this. And here is the results on the test set. So as you can see, the NER approach performs much better than the text summarization in terms of both Rouge 1 and Rouge 2 scores. And then we did human evaluation. As I said, it's common to do human evaluation in text summarization problem. So we select 1,000 random samples from the test set, and we ask the crowd workers to manually summarize those titles. And then we, again, ask the crowd workers to rate 4 versions of the show titles side by side on the scale from 1 to 10, with 10 being the best title, best meaning short but descriptive, that you cannot remove anything from the title to make it even shorter without losing original meaning, and 1 being the worst. So the 4 short versions are the ground truth from the abstract text summarization model, and then the second version is the show title that we compose from the NER predictions. Remember, NER predicts entities, not the actual show titles. And then the third version is the show title from the text summarization model itself, the prediction itself. And the last version is the human summarization. And here is the result of the average rating. Remember, the scale was from 1 to 10. So as you can see, text summarization is much worse than the other 3 versions. And we did statistical testing that actually it is significantly worse than the other 3. And the other 3 versions, I mean, by looking at the numbers, there seem to be some differences, but actually there's no statistical difference in in those numbers. So That concludes my talk. So in summary, we reviewed NER and the text summarization approaches and some of the latest advancements in NLP. We talked about how we summarize the product titles using these two approaches. And also our evaluation results show that NER performs much better than the text summarization for this particular problem. Thank you for your time.